We're going to see a small example on KCL and KVL in this video. Have got a circuit with Vn, the voltage source, and resistors R1, R2, R3 connected in this pattern. And this pattern of arrangement is called the series arrangement. Why? Because when the current I is going to be the same in all the elements, and all the elements saw the same current is flowing. If the same current is flowing on all the elements present, then we call the elements to be in series. So same current I is flowing in all the resistors. Why? Because there is no division of current here. There is only one path to flow. So the same current has to flow all in all the paths. So I can call this R1, R2, R3 are in series. Okay, that is good. And now we are asked to find what is the Vn. Indirectly, I am asking you to say asking you to find the Kirchhoff's voltage law equations, or the voltage equations using Kirchhoff's voltage law. So I want you to do that. So let's try together. So first thing we always do when we're doing the Kirchhoff's voltage law or the Kirchhoff's voltage equation is that we have to assume the polarity of each element. When the current I is flowing, what is the polarity, or what is the voltage drop across each element? Each element here is resistors. So what will be the polarity when the current I is entering here? Because a resistor has a property of voltage drop, having a drop in voltage when current enters. So it's a plus and a minus. So plus and a minus, it is ending with minus. It's a drop in the voltage. So the voltage drop here is in this direction, in this polarity it's going to have. So similarly here the current is entering at this point, so it's plus, and it's leaving here with a drop, so minus. Here also it's entering here with a plus and leaving here with a minus, so it's a drop. So all the elements are having some voltage drops, and I've indicated the polarity across each element. What is the polarity? The polarity of the voltage drops across each element. And now already in the voltage source we have the plus minus, so there's no need for us to assume anything because they've already given the polarity here, the voltage. So that's good. So let's write what is the Vn equation now. So now I'm going to start my analysis from this point. Okay, from this point I'm going to go in the clockwise direction. Okay, let us do our analysis. The above arrow mark is my analysis direction, the direction which I'm going to do my analysis. Okay, so here it's Vn. So starting with Vn, a plus, it's a minus and a plus, so it's ending with plus. I can say it's plus Vn. So it's a plus Vn, and here it is a plus and minus, ending with a minus. I say it's a drop, right? So drop, it's minus. What is it? What is the voltage? V equal to IR. So V, it is I into R. The current is I, and the resistor value is R1. So I into R1. Okay, and the next one is I into R2, but it's again ending with a minus. I will take it as minus drop, right? So minus I into R2, and similarly for the last one also it's minus I into R3. And because the whole loop is completed with the R3, it's again coming to the same point. I started with this voltage source, and I'm coming back to the same voltage source, right? It was plus Vn, so it's done. So whole loop is completed. So the whole voltage drops in the circuit in a closed path is going to be 0. The sum of all the voltage drops in a closed path is equal to 0 according to the Kirchhoff's voltage law. So this is my equation. You can further simplify this equation by taking the I common. So Vn will be equal to I into R1 plus R2 plus R3, or Vn equal to, yeah, that's all. Vn equal to I into R1 plus R2 plus R3. That's what we'll get for Vn. Okay, when you further solve this equation. So this is for the KVL we did. Now let's look into this example. It's a very simple one, and we have got a node here, and the voltage source is present here with the plus minus, and 4 amp current is entering in this node, and I2 current is leaving, and again 2 amps is also leaving. So we need to know what is I2. So we know that the sum of the entering current should always be equal to the sum of the leaving currents. So what are the entering currents? There's only one entering current here, that is 4 amps. So 4 amps is the only entering current here, and there are two outgoing currents. So 4 amps, 4 amps is the incoming current equal to the sum of the outgoing currents. Sum of the incoming currents equal to sum of the outgoing currents. Outgoing currents are the I2 and 2 amps. So I2 plus 2 amps. Okay, good. So now what will be our I2? I2 is 4 minus 2, which is equal to 2 amps. Okay, we're done with what is I2. And one more thing, whenever we see a node, we know that there will be an at least one incoming current and at least one outgoing current. Other assumptions can be done anyway, or any side, any directions we can assume. But there can be a possibility like this also. Theoretically, not practically, but theoretically, there can be a possibility like this. All the currents assumed may be like entering. If you're having a node and all the currents are entering like this, what we can say, suppose if it's I1 and then I2 and then I3, all the three currents are entering, then what we can say is the current in this node must be 0. This is what our KCL says. What our KCL says is there must be no residual current at our node. So that means the sum of all these currents, I1 plus I2 plus I3, must be equal to 0. So this indirectly means that one of the currents here is negative, or it's going to be in opposite direction. So if we get I3 equal to minus 5 amps, that means what the direction of I3 is not actually getting inside, it's actually going outside. Practically there will be at least one incoming and one outgoing in a node. But theoretically, when you assume such a condition, we'll make it add up to 0. Or the same way, when we assume all the currents as leaving, then also we can say if all the direction of the currents here is entering, right? Instead of that, if I assume as all the currents are leaving, then also I can say all the sum of all the leaving currents equal to 0, because there's no incoming currents. That's what I'm trying to tell you. But practically it's not true. Practically we might get a value of I1 or I2 or I3, either some of them or two of them, to be negative, which indicates that at least one outgoing current is there and at least one incoming current is there. Okay, that is a theoretical understanding. That's fine. And now let's have one more thing. It's again the similar thing. I2 equal to 6 amps. So 6 amps current is coming from this node, and 3 amps I3 equal to 9 amps. So 9 amp current is flowing here. And what is our I1? Oh, I1 is here, sorry. I2 is 6 amps. So 6 amps is flowing here. It's not flowing there. Okay, 6 amps is flowing there. Okay, so good. So what is I1? So what is this incoming currents? There are two incoming currents here. I1 and I2 are incoming currents. I1 I do not know, so we have it as I1, and the another incoming current is 6 amps, that is I2. So I have I1 plus 6 amps equal to our outgoing current. Only one outgoing current at this node, that is I3. So I'm looking at this node, I'm talking about in this equation. So it is I3. I3 is 9 amps, so 9. So what is I1 now? That was asked, right? I1 equal to 9 minus 6, which is 3 amps. Good. So we have 3 amps to be our I1 flowing. So this is the a practical understanding of KVL and KCL. And let's continue learning in the next lessons. Thanks for watching.